Distributed tracing is incredibly useful when you're building distributed systems. When you've got these disparate things that are all running independently, all communicating completely asynchronously, being able to understand how requests flow around your system is incredibly important. But I'm sure you've all been in a situation where you've got maybe fantastic distributed tracing, you've got structured logging, but you're really struggling to understand how your system is performing as a whole. Stepping back and taking that macro level view of, is my system doing the thing that it's supposed to be doing? And that's where generating metrics becomes really useful. Metrics allow you to take that macro level view of your entire system. And by the end of this video, you're going to know exactly which metrics you should care about when you're building asynchronous systems. Let's get into it. So when it comes to building event-driven systems, there are a subset of metrics that you should care about. Now, obviously, this video isn't going to cover every possible metric you could possibly monitor, but I do want to cover some that I've found particularly useful when building event-driven systems in the real world. And thankfully, Open Telemetry actually publish a set of semantic conventions for messaging metric. If you've watched my previous video on semantic conventions, you'll know these are simply standards for the kind of things you should care about with your telemetry. And actually, Open Telemetry publishes a set of common metrics, producer metrics, and consumer metrics. And there's not actually that many things in here. The operation duration, the number of messages sent, the number of messages consumed, and how long it took to consume a message. So there's only really 4 things currently in the semantic conventions for Open Telemetry. Now, I want to introduce you to a few more. And I don't want to go through all of these in absolute detail. I'd rather get in and actually show you how you can generate these metrics using your telemetry. But there's some quite interesting ones in here. Things like the queue depth. How many messages are there in a given queue? If this is your actual application queue, this could indicate that your system can't deal with the required throughput. If this is your dead letter queue, this probably means there's a problem. You've then got the published and consumed count. You'd have seen this in the Open Telemetry semantic conventions, but I also think it's really interesting to monitor the size. What is the average size in bytes of the messages that are being published in your system? A massive spike in either direction of message size could probably indicate that that message has actually changed. Something structurally about that message is now different. The age of the message, how old are the messages you are processing? If you're finding that the message age is consistently creeping up over time, this again could indicate that you can't deal with the throughput of the system. Your consumers simply can't deal with the throughput, so you're getting this ever-growing backlog in your age of message that you processed. In-flight latency, how long does the actual message transport add to the overall processing of the event? And then finally, some pretty common ones, the number of errors and the number of types of each message. Now, again, this isn't an exhaustive list of all the metrics you should care about, but there is a good subset here that would get you started. Now, when it comes to actually generating these metrics, there's 2 very clear differentiations that I want to make. The first is that any of these metrics related to your actual application itself, things like the average size of the message, this is something that you can generate in your application. In almost all cases, those metrics can be generated from aggregating your trace data. If you've implemented the semantic conventions that we talked about a couple of videos ago, actually all of these metrics related to your application, you can generate from simply just aggregating your trace data. Let me show you what I mean by aggregating your trace data. And if we actually go to your observability backend, whatever that might be, you run a query across your trace data, providing you've got these semantic conventions, you can say things like, show me all of the spans where the message operation type is process. Process would be the semantic convention for a consumer. Aggregate that by message type, and I can now see that there are this many spans, this many product added events have been consumed, this many user created events. If you were to switch that to publish, which is the semantic conventions for the producer, I can see how many of each different type of event was produced. And maybe if you're a developer on a certain service, I could narrow this down to the inventory service, and I can see here are the number of events that the inventory service has published, and equally, we can also have a look at the number of events that the inventory service is consuming. So just by having these semantic conventions and having these really well annotated traces, we can start to aggregate this now to draw this really interesting high-level information. If we also look at the message size, we said before, if a massive spike in message size in either direction, up or down, probably indicates that the format or the structure of the event has changed. And we can have a look at this here and see, actually, what we would probably expect is a straight line a little bit like this. In most cases, you might get a little bit of variability, like a byte, maybe a few bytes, but in most cases, events are going to be pretty similar sized. We look at this stock reserved and stock reservation failed events up at the top here, And there is a little bit of differentiation there, 908 bytes at this point, and then down at the bottom here, 784 bytes. So we're seeing a little bit of movement there, but only like 120 bytes. If we keep moving through things, we can look at the message age now. So again, we're doing a similar kind of thing. Instead of looking at the average though, let's have a look at the P99 of message age. What is the oldest message that we've processed? And we can see that the user created event has got this really interesting big spike. The user created event processed a message that was 3,120 milliseconds old, but then immediately dropped off and actually came down to 100 milliseconds and 200 milliseconds. So that's probably not too much to worry about. This system is running with AWS Lambda. Honestly, that was probably some kind of cold start or some kind of polling behavior in Lambda polling SQS. Because of that big drop off, not too worried about that there. And the final one I want to look at is this duration. How long did it take to process a message? Here we can do a similar kind of thing. We can look at all the spans that have an operation type of process. Give me the P99 this time of the span duration. I want to see what's the 99th percentile of how long it took a process span to run. And we can see we've got these two reasonably big spikes here for the user created event. It took 940 milliseconds. If we wanted to, we could kind of zoom into this a little bit and have a look at the actual traces. We've got this one big outlier here that took 2.4 seconds. And if we drill down and have a look at that, we can see that that looks like that was a cold start on the Lambda function. So we can, now that we've got this high level information, you've got this ability now to zoom in and zoom out. Because you're aggregating your trace data to generate these metrics, you have this ability to zoom in to investigate something interesting, investigate an anomaly, and then zooming back out to see how that fits into the bigger picture of the system. So like I said, anything related to your application, the size of messages, the number of messages, get the semantic conventions in your trace data and then aggregate your trace data to generate the metrics off the back of that. If we think back to that list of metrics I had on screen earlier, one of them was queue depth. How many messages are there outstanding in a queue? That's something that is related to your infrastructure, not related to your application. Similarly, for a Kafka topic, what's the current offset for a given consumer in a Kafka topic? That's something that is in your infrastructure, not something that is in your application. And it's this scenario where the more typical metric type setup would be more beneficial. Actually pulling metrics from your infrastructure and pushing them into your observability backend will allow you to get this deeper level of information. If you come back to your observability backend, now we can have a look at a metric here that we have for the approximate number of messages visible. This is a metric we can get from SQS. You can get this from CloudWatch itself inside the AWS console. And we can do a little bit of querying here. We can say, I want to see all the queue names that contain the word DLQ. And I want to look at the average number of messages available by queue name. There actually, thankfully, haven't been any messages in any DLQs across my system, which is kind of a nice place to be. But you can see down at the bottom here, if we have a look at this list of queues, you can see this is basically all of the DLQs across the entire system. If you wanted to, you could filter this even further to look at things for a specific service based on the tags that you add to your metrics that you send. We could equally do this as well to look at, instead of doing queue name, we could say where the queue name doesn't contain DLQ, and that gives us a list of all the messages that are outstanding in the actual queues themselves. These are the real application queues. So what you're doing here is you're using the actual infrastructure metrics that are pulled from your infrastructure to take a slightly different view on how your system is actually performing. And when you start to bring all of this together now, you can bring all this together into these really nice dashboards. So you can see we look at over a given time frame, we can see some really high level numbers about how our system is performing. There's 8,000 messages processed, 5,000 messages have been published. You would typically always expect your published to be higher than your processed because you might have 3 consumers for the same event, which is probably what's happening here. There's maybe 3 different consumers for the same event type. We can see the average size of the bodies, we can see the time, we can see the messages being processed. And then we've also got these infrastructure metrics down at the bottom here as well. You're looking at the DLQ message counts, which we know are 0. We've just had a look at them. But you're also looking at a different metric inside SQS to look at the message age inside a given queue. And you'll see now that the system's not actually running at the minute, which is why this is flatlined. But earlier on today, you can see that the average age of a message inside the product created event queue was 19 seconds at some point today. Again, if that number was creeping up and up and up, or it was pretty constantly high, that potentially indicates that there's a problem dealing with the throughput that the upstream systems are imposing upon you. The big takeaway here is having those semantic conventions, having that element of standardization inside your telemetry that your application generates. Hopefully that's distributed tracing. You can then use that to aggregate together and actually generate these metrics from the data that you already have. This has a twofold benefit. One, you've just got one lot of telemetry to care about. When you're writing application code, you just care about traces, adding attributes to your traces, knowing that down the line, you can aggregate that in different ways. That also really powerfully gives you that ability to zoom in and zoom out. If you know your metrics are being generated from trace data, well, if you see a big spike, a big anomaly, you can actually zoom in and go and look at those individual traces. What are the traces that make up that anomalous number before zooming back out again and having a look at that bigger picture? And then for anything infrastructure related, that is where real traditional metrics become really powerful because you can't generate trace data from your SQS queue, but you can look at the metrics that SQS gives you, or Kafka or SNS or whatever the service happens to be that you're using. You can pull the metrics out there. So I'd really encourage you to think about them semantic conventions. Go back and watch the other video in this series if you haven't already. Look at the semantic conventions and how you can start to add some of that to your telemetry in your applications. This is going to be an ongoing series about building and observing systems. I will see you all in the next one.